Auditing force calibration labs, how to help labs better their measurements. Welcome to this presentation here. This was going to be giving at the A2LA technical forum in 2020, but due to COVID-19, that forum was canceled. They really wanted to get this information out to everybody because if you're home, or even if you're not home and watching this at a later date, this is really an important topic because you can look at this and you can view it from your point of view as a lab. If you're watching this, you can view like, how do I make better measurements? Or how do I pass my next audit? How do I make sure everything I'm doing is compliant with the standard? And as an auditor, if you're viewing this, you can look at this. What are labs doing that they shouldn't be doing? How many of them are making these measurements where they think they're in tolerance, but they're not? So different combinations, different way to view this. And it all goes along with our purpose, which is we create a safer world by helping companies improve their force and torque measurements. It's really something we're passionate about. It's something that, for our kids, selfishly passionate about as well, because for our kids, our families, our brothers, our children, our, cousins, grandparents, parents, whomever, is if people are making better measurements, the world becomes a safer place. And with the world becoming a safer place, we have less mortality, less death. And that's really what we want to avoid. We don't want anybody dying because someone failed to make the proper measurement. So that's part of all of our education, part of our purpose, and we hope this comes back. Obviously, we hope this comes back to us as we feel we know exactly what we're doing in regard to force and torque measurements, and we can give companies more confidence if they come back and use Morehouse. But let's talk about auditing force calibration labs. Let's talk about the agenda. We'll talk about ASTM E74, standard violations to look for and correct, asking the right questions, the importance of adapters, the right equipment, and the right calibration provider for your equipment. Now you're starting to listen to this and wondering, what's the outcome? Well, the participant will be able to have knowledgeable discussions about the right questions to ask, what constitutes good force measurement equipment, adapters used for force calibration, all of which should allow whomever is in this audience to improve your capability or provide recommendations to make the lab they are assessing better. So if we start talking about E74, before that, we're going to talk about how some additional material. We have technical papers on adapters, uncertainty propagation, technical paper on E74 and ISO 376, technical paper on risk, technical paper on aircraft and truck scale calibration, PDF version of this presentation. All of which, if you go to mhforce.com, click on press, P-R-E-S-S, you will find the link for technical papers where you can pull these and many other papers. So lots of good resources at mhforce.com. Documents, jumped ahead of myself. The documents referencing E74, the standard. We're going to talk about E74 first, but here are some documents, a list of them. There's AASHTO T22, AASHTO T68, ASTM E4, ASTM C39, E10, and E18. If somebody is doing verifications to E10 and E18, their specific needs call out to have the force measuring device calibrated in accordance with ASTM E74 using deadweight primary standards. So basically what this is saying, it's in section A 2.6.2.1 in E18, and there's similar wording in E10. Test accuracy ratio, this term should be dead. It lives on in E74 because it is a standard, and we as a committee and as a standard, ASTM as a standard organization, can control what happens here. So you have primary standards at the top. They're required to calibrate secondary standards. Primary standards can be used to calibrate working standards, as this will often result in the lowest possible loading range. Secondary standards are required to calibrate working standards. They cannot calibrate other secondary standards, and working standards are used to calibrate the testing machine. So there I have, it's a simple pyramid here. So I need at least a working standard to do my testing machine. If I want a working standard calibrated, I need to have that with secondary standards. And if I need a secondary standard, I need to have that calibrated by primary. So for instance, Morehouse, our company, offers deadweight calibrations up to 120,000 pounds. So we can supply customers with secondary standards class AA range of forces from basically 0.1 pound to 120,000. Now, after 120,000 pounds, we use a standard, a 1,000,000 pound standard that was calibrated by NIST. We can supply only class A because we have a secondary, we can only supply class A for any measurement over 120,000 pounds. We also have 3 1 million pound load cells that go to NIST, so we can apply, class A calibrations up to 10 meganewtons or 2.25 million pounds. What we cannot do, we cannot take that 2.25 million pounds and give a class AA range, which is in here. No one in the world can give a AA range because it requires primary standards, and the largest machine is located in Gaithersburg at NIST, and it is a 1 million pound deadweight machine. Lots of recent articles about it. They're all great about how they recalibrated the weights, tore the machine apart. Really, really cool stuff. Anyway, so if we start going into this primary force standard, what is it? It is a deadweight force applied directly without intervening mechanisms such as levers, hydraulic multipliers, or the like, whose mass has been determined by comparison with reference standards traceable to national standards of mass. To be classified as a primary standard, the weight shall be determined within 0.005%, that's 50 parts per million, of their values by comparison with reference standards traceable to the International System of Units, that's SI for mass. This is found in ASTM section E74 6.1.2. Now, it's not simply just mass. It's weights that require for the effects of local gravity, air buoyancy, and like we said, they must be adjusted to better. Most states can do better than 20 parts per million. And the weights shall be made of rolled, forged, or cast metal. Adjustment cavities should be closed by threaded plugs or suitable seals. External surfaces weights shall have a roughness average of, 3.2 or less as specified ASTM B46.1. Stainless steel materials preferred because it's not magnetic. The local gravity adjustment, the best thing you can do is have the local gravity surveyed. In the end, what you're going to do is you're going to adjust to the local gravity, air buoyancy, everything else, and you're going to realize at our location it's something like 1,000.7 pounds equals 1,000 pounds of force. And then we're going to also make adjustments based on height. And we're going to do lots of different things in that, but just a general overview is what is a primary standard, and that's what it is. Now, secondary force standard is pretty simple. An instrument or mechanism, the calibration which has been established by comparison with primary standards. In order to perform calibrations in accordance with ASTM E74, your force standard must be calibrated with primary standards. People that are not getting their standards calibrated by primary standards cannot go out and assign another Class A loading range, which we will talk about later. Some examples of machines. All of these are Morehouse machines. We have our universal calibrating machine. Standard here, calibrated by deadweight primary standards. This one's a 100,000 pound machine. We put it in our deadweight machine. We calibrate it. This standard here can calibrate other load cells and assign a Class A range. Here is our bench top. This is a 10,000 pound machine capable of 10,000 pounds, and it's a nice portable unit, somewhat portable unit. The weight is around 150 pounds, but it can be sat on a bench top. It can be rolled around. And then we do have a portable unit, which is our little, smaller 2,000 pound Morehouse PCM. All of these, if you see, you can see the load cell, all have load cells which have been calibrated by primary standards. So therefore, they can calibrate to E74 and assign a Class A range. They can also calibrate all these other devices seen in the picture: handheld force gauges, Dillon dynamometers, tension links, all of that stuff. Now, this portable machine was built for a reason, and that's ergonomic, and it's a lot easier to calibrate these handheld force gauges with this PCM in tension and compression using the proper adapters, as it is opposed to stacking like 250 pounds of weights and playing Jenga. So it solves a very ergonomic issue and improves the safety of technicians. Secondary force standard, the range of use is limited by the verified range of forces established by the standard. ASTM E74 Class A verified range of forces for calibration of secondary standard load cells. It's basically found by multiplying the lower limit factor by 2,000. And this gives us a 5-to-1 ratio. when we look at what's actually going on. And then we look at the ASTM E74 Class A verified range of forces for calibrating of a testing machine. This is found by multiplying the lower limit factor by 400, which gives us a 4-to-1 ratio. What's going on here is you will go into it. You go into, make your measurements. You take a lot of measurements, and then you calculate the standard deviation of all the deviations. You get a lower limit force factor, and you multiply that lower limit by 400 at that specific point, that first point in the Class A verified range of forces. Your TAR is exactly 4-to-1, and the range of use of all these cannot be less than the lowest applied force. This is not a zero force. This is the lowest actual applied force. Loading range cannot be less than 400 for Class A or 2,000 for Class AA times the resolution. So if I have a device with a 1-pound resolution and I want a Class AA loading range, the first point that I can take as a calibration at our facility is 2,000 pounds. I cannot take 0 as my first test point. It is not allowed. So at least if we're looking at the procedure, at least 30 force applications are required. We typically run 3 runs of 11 or 33 force applications. This is pretty simple, simplistic, because we want that point below 10%. Most labs are just doing 10%. Hey, I'll take 0 and then 10%. That's not correct. If an instrument is not calibrated, if you take 0 and then 10%, the first point you can use in that range is going to be the 10% point. So you really can't use that device below the first non-zero calibrated point. And then there should be at least 1 calibration for each 10% interval throughout the loading range. And if the instrument is to be used below 10% of capacity, a low force should be applied. This low force must be greater than the resolution of the device multiplied by 400 for Class A or 2,000 for Class AA. If we look at the procedure, it's pretty simple. Allow the UUT to come to room temperature, often a day or more of saturation in the lab. Warm up instrumentation. Normally, if you're going to power it on, normally 30 minutes is enough. Select 10 to 11 points. In this example, we have 11, starting with 200. Fixture the UUT in the test frame. Exercise it 2 to 4 times. Then apply your first series of forces. Rotate the UUT 120 degrees if possible for run 2. If it's tension and compression, you're going to want to start with one mode, probably compression, switch to tension, run all of your tension cal, 0 degrees, 120, 240, and then switch back to compression. So that's what's going on here. We're doing that when we talk about deviations. We have newer certs in this, but I like these certs because they show everything right here. It's as far as the deviations from the fitted curve. We're going to start looking at these numbers. We're going to do a curve fit. We're going to do a generate polynomial. We're going to generate coefficients that best fit the curve. That's going to give us the values from the curve. And then we're going to look at all these, from these values, we're going to take the deviations from each of the observed points, which is basically the values for the fitted curve minus, values from the fitted curve minus what we actually observed during calibration. So we're going to take all of that, we're going to sum the squares, and then we're going to multiply it by 2.4, which corresponds to roughly 98.2% confidence. And we're going to base everything on the lower limit factor resolution. If I have a if I have a resolution of 1 pound and I'm Class AA device, 2,000 pounds is my first point. It could be where I have coarse resolution, where 2,000 pounds, where my lower limit factor, I have coarse resolution, my lower limit factor is actually less than, the 2,000, the lower limit factor multiplied by the, 2,000 or 400 is actually less than the lower limit factor. And therefore we would have to use the first test point or the resolution times 2,000 versus the lower limit factor times 2,000, whichever is higher. And then another thing I wanted to note here is recalibration is required for a permanent zero shift exceeding 1% of full scale. We get asked this question a lot. This is per the standard. So customer has a device, they overload it. They're not sure how much they overload it. The load cell still works. They think everything's good. They send it in for cal, and then we see this large shift in the data. The whole reason that large shift of the data can put them way out of calibration, but this is the whole reason. If you think you've overloaded a cell and you have a shift by more than 1% of full scale, it needs to be recalibrated. There's good devices on the market, such as a load cell tester and some other things that can easily test this. Calibration interval, question we get asked a lot. This is in section 11.2.1. Force measuring instruments shall demonstrate changes in calibration values of the range of use during the recalibration interval of less than 0.032% of reading for force measuring instruments and systems used over Class A verified range of forces, and then 0.16 of reading for those instruments using a Class A verified range of forces. Force measuring instruments not meeting the stability criteria of 11.2.1 shall be recalibrated in intervals that shall ensure the stability. So basically what the standard says, if you meet this criteria, you can have a 2-year recalibration interval. If you do not meet this criteria, you have to shorten the interval so that you meet. Lots of people will shorten it to a year. Maybe you'll meet at 14 months. Maybe a year is too long. Maybe it's 6 months. So the standard puts it back on you to ensure that you're going to meet. So there is a judgment call here. We see lots of people that if it doesn't meet, they go to a year, then it meets, then it goes to 2, then at 2 it doesn't meet, then they go back to a year. We see that happen quite a bit. And then it is recommended that the lower force limit be not less than 2%, 1/50th of the capacity of the instrument. Here's the 10,000 pound load cell looking at the first point, that's 2%. First 7.2.1, this is what I've been talking about. If the lower force limit of the verified range of forces of the force measuring instrument is anticipated to be less than 1/10 of the maximum force applied during calibration, then forces should be applied at or below this lower force limit. In no case should the smallest force applied be below the lower limit of the force measuring instrument as defined by 400 times the resolution for Class A and 2000 for Class AA. Here we get a situation. You can say what's wrong here. You have, if you're looking at the data, looking at everything that's going on, what is wrong here is simple. We have a first test point of 500 pounds, and we have a Class A lower limit of 192.3. ASTM clearly says the verified range of forces shall not include forces outside the range of forces applied during calibration. So 0 cannot be your first test point, simply cannot happen. This cert would be in direct violation with the ASTM E74 standard. And there you can see in more detail standard deviation, lower limit factor 0.48, 192. Since the first force point was the first non-zero, remember 400 times the resolution, or 2000 times the resolution. Since the lowest point was 500, you cannot use this instrument below 500 pounds. What else we see happen? Do not assign a class or Class A verified below the first non-zero force point. They're the two sections, 8.6.2 and 7.2.1. The 8.6.2, the verified range of forces shall not include forces outside the range of forces applied during calibration. Look, we've read this. Here it is. It's clear. Labs that are doing this are in violation of the standard. Just wise up. If you have a cert that says your lower limit is less than the first non-zero test point, that cert is incorrect. Secondary for calibration in accordance with E74 secondary force standard. This is the one that, remember, has been established by comparison with primary criteria, lower limit. This is just another example. Here we have a calibration standard. And if we look at this, what we really want to show is they're using secondary standard load cells and assigning a Class AA range. This should never happen. Just not something you want. There again's the load cell that's happening. This is the older example, but it still happens. So this is not, calibration lab is using a load cell. Cannot assign Class AA with a load cell ever. So check that. Check your scope. Make sure, check your cert, check the scope of the lab. If the lab does not have primary standards, they cannot assign a Class AA loading range. Other things: do not assign a Class AA verified range of forces unless you're calibrating with primary standards accurate to better than this 50 parts per million. Do not assign a Class A verified range of forces unless you're calibrating the device using a secondary standard that was calibrated by primary standards. So you need a Class AA. Your certificate absolutely has to say Class AA verified range of forces for you to calibrate other load cells in accordance with ASTM E74. So a force measuring instrument with a Class A verified range of forces cannot assign a Class A verified range of forces. A force measuring instrument with Class AA cannot assign Class AA. If we look here, more examples of scopes you find on what's wrong. This is really interesting. So not only are they referencing torque in the wrong units, torque is absolutely force times length, right, people? No one ever says meter Newton. It's Newton meter, so it should be pound inch. Not only are they mentioning that wrong, but here's an example where they're referencing ASTM E74. This is not the standard for torque. There's clockwise here. Nowhere near the standard for torque. Torque is ASTM E7428. So wrong standard completely. Someone got away with this. It's a shame. Then here's another one. This one, great. This is our company. Morehouse gets identified. We don't even do a calibration for this company. This is poor. This is to certify that it has been calibrated against a load cell, traceable to NIST, dead weight standards. Great. So how far are they away from dead weight? All readings are within a tolerance of 0.1% of applied or 5 pounds, whichever is greater. Load cell calibration with calibrated, next calibration due. Accuracy of the load cells using the calibration presses are maintained at better than 0.025% accuracy. These are actually direct basic standards certified by Morehouse Instrument Company using dead weight machines trade. So essentially, ASTM spec E7402. Wow, that hasn't been updated in a long time. And this is a recent cert. Look, it's due August 2019. This was calibrated in 2018. The ASTM standard they're referencing is E7402, which now we're at E7418. There was an E7404, an 06, a 13. This company is just non-compliant at all. And basically they're saying, hey, we go to NIST. We go to NIST, right, through Morehouse, but Morehouse doesn't do our cal. Morehouse's customer of Morehouse, does our cal, and we're way down here. So if we look at this pyramid, you can start seeing it. NIST, awesome. NIST is great. Morehouse, little bit, NIST is at 5 ppm. For their 5 ppm, we're at like 8 ppm. Morehouse customer, let's get Morehouse customers actually at 04. Wow. And then here we have this outfit, which I know who they are. So we have them down in here, right? Morehouse customers' best capability is 0.04%, around that, and they are saying that they're maintained to better than. I can't even follow this anymore. This is just poor. If you have a cert that looks like this, stop using the company. It's not good. Nothing is right here. So machine traceable to NIST, it's traceable to SI. We can go on and on and on and on. So like I said, what's interesting here is we don't perform the calibration for this company. ASTM's current version is 18. And the company using is, as I said, 04, but it's 037, and they're claiming it's just pure ridiculous. This needs to stop the whole way through. There's nothing good about this example and the company doing it. So ASTM E74 is not ISO 376. We have a whole class on ISO 376, a whole presentation, but ISO 7500-1, calibration and verification of static uniaxial testing machines required standards to be calibrated in accordance with ISO 376. You simply cannot use the ASTM E74 calibration to perform an ISO 7500 calibration. ISO 376 has several requirements that are not requirements of ASTM E74. Some of these requirements are as such. You have ISO. Well, let's look at this. So basically, ASTM E74 is doing a lot of things well. And one of the main, that lower limit factor, and what we're doing here is really quantifying what I like to say the expected performance of the device, assuming it's used at the same temperature, under the same loading conditions, everything else. We can stick that in our dead weight machines, that load cell force measuring instrument in our dead weight machine. We can get a very good, by rotating the instrument, a very good reproducibility. However, ISO 376 also requires repeatability. This is found by putting the instrument in the same location, taking 2 series of readings without rotating, without touching, without doing much of anything. Then we have interpolation. We have 0, how well it comes back to 0. Reversibility isn't always there. That's only if you're using the calibration for descending. And if I back up here, if you're using the calibration for descending, you need to have it calibrated descending. And then if you don't use reversibility, you can do a creep test, and then it has the expanded uncertainty of the applied force. So if my uncertainty, which it is, of our million-pound standard is better than 0.1, I can assign a class 00 range. Ideally, I want dead weights, but I'm limited on my 0.01. We can only do that for partial parts of the range, and then we have to pick it up with dead weight. So million-pound calibration comes into us for ISO calibration. We can do class 00 to X, and then we'll pick it up again in dead weight because it's based on expanded uncertainty. Anyway, it's just not the same as ASTM E74. If we start looking at uncertainty, we have another session, papers, classes on this. Looking at uncertainty, here's what we want to consider. The ASTM lower limit factors, the type A, it's by statistical analysis, repeatability of the best existing device, repeatability and reproducibility, and then we have type B, resolution of the best existing device. Going to need to do some type of test. We need reference standard resolution. If dead weights, we're not going to have resolution. Reference standard uncertainty. Stability is huge. A lot of people forget to put stability. We have numerous customers send us in instruments and say, hey, calibrate this to an accuracy of 0.1% of applied. We calibrate the cell. It obviously from the last year has changed more than 0.1%. We adjust it back in. I look at the company scope and they say they can do 0.1%. They're just simply not accounting for reference standard stability, which needs to be accounted for. Environmental factors and other error sources. And reference standard stability can also be type A in there. And then we have this great spreadsheet. This is just a quick example. We have this great spreadsheet. You type in all this information and it just gives you the little red arrows at the top, guide you through things. You type in all your information from your cert. You have to do your reproducibility, repeatability, and other stuff, and then you can use that information to do a full uncertainty, and hopefully we've simplified that process. So asking the right questions. Are you discussing customer requirements? We've switched off of E74 to someone sends you in an instrument. What are you going to do? What specific things are you going to do? And these things starts with asking the right questions. And some of these questions are, to what capacity? What mode or modes? Compression, tension. To what standard or customer request? It's, we just talked about E74, ISO 376, commercial 5-point, commercial 10-point. What are reporting expectations? SEB, that's static error band, nonlinearity, hysteresis, tolerance requirements and decision rule. If you're accredited, you better be asking this. A lot of people miss this one. Does the calibration require ascending, descending points? How about multiple bridges? Do you have a calibration due date or frequency you want to put on the certificate? If in accordance with a standard, we can assign a due date. Otherwise, customer is responsible for the due date. How is the instrument currently being used? This is where we get to adapters. How are you using it? We want to replicate how you're setting it up. Otherwise, it's garbage. You don't send it to us for cal. Don't send it anywhere for cal. You say you're required to get it calibrated, but unless the lab doing it is replicating how it's being used, you're not going to get the same types of results. And then here's a catch-all, because we really have, this is that 20% of the 80-20 rule. This is that 20% of the questions that are going to get you 80% of what you need. There's a lot of other questions to ask as well, but you don't want to overburden. Sometimes you just don't want to overburden people with them. So when I said about the decision rule, there it is. 3.7, a decision rule is defined as a rule that describes how measurement uncertainty will be accounting for stating to a conformity. And then we have 713. When a customer requests a statement of conformity to specification or standard for the test, calibration, pass, fail, in tolerance, out of tolerance, the specification or standard, and the decision rule shall be clearly defined. This can be simple acceptance, but you have to have the discussion. And if you don't have the discussion, I have a little bit of guidance here. And my question is, are you clearly defining the decision rule with the customer? So if you're not, since it's not always talk to the end user, we personally have done a two-part system. Part one, every quotation out has this: instruments which have specified tolerance will have a guard band applied per method 5 of ANSI Z540.3 handbook. Sending an instrument in for calibration is acceptance of these terms. This is on every quotation that we send out. Try to work with all customers and offer other decision rules, such as simple acceptance and method 6. Hey, we can do that. If we can't reach out, if we send a quote, someone doesn't know the decision rule they want, we're defaulting back to method 5, which is taking the measurement uncertainty into account and just subtracting it. There's other methods. There's method 6, so many different ones. I just recommend, it's a free document, recommend reading ILAC G8 09 2009 Guidelines on Decision Rules and Statements of Conformity. So some of the things that were highlighted that are big error sources is, does the calibration require ascending and descending points? Back to E74 is 7.4.1 and 18. This is a new change. Force measuring instruments are usually used under increasing forces, but a force measuring instrument to be used under decreasing force, it shall be calibrated. This was in the notes section as it should, and it became a shall. So no longer are weasel words in the standard as far as descending. If you're using it for descending, you must have it calibrated in descending. And I took one of the best 100K load cells. It's one we use in our secondary standard to do really, really large crane scales. And I compared this. I compared the output on the ascending curve versus the descending curve, and I got an additional error of 0.042%. And that's on one of the best load cells. This load cell has like a 2-pound lower limit factor. Just really, it's actually, it's lower than that at times. It's just really, really low. 2 pounds out of 100,000. That's low. And we still had a 0.042%. So if I use this cell and I don't have it calibrated in descending, and I make descending measurements, I'm going to be off, and it's not right. How is the instrument currently being used? No one's giving really, I haven't seen many people give guidance on this, but this has a lot of impact. This can have a lot of different scenarios. And the most common are what adapters, here's more questions. What adapters are used with it? How is it loaded? Is the force device loaded through the top shoulder or thread loaded? If loaded, how much engagement? Is the force device loaded through the bottom threads? Do you have a top block that can be sent with the measuring device? And here's what we did. Here's a simple test. This is a load cell, a rather good load cell. Output was 10,001.5 pounds with an 1.5 inches of engagement. It was 9942.3 with 1/2 inch engagement. And some people can say, well, this is pretty simple. Use a 1.5 engagement. But if the customer sends you nothing, and if you're the person that's sending your equipment out without anything, or you're auditing a customer that's doing this, and you see holes in their load cell, say, where are the adapters that thread into that? Are they being sent with the item for calibration? If not, why not? For all we know, they could be using a 1/2 inch adapter, and that error, the measurement error was 0.5% on a device expected to be better than 0.025, 20 times what was expected. How about loaded through the bottom threads? Our competitors like to set everything up. One machine, they do a calibration in 5 to 10 minutes, get everything done, compression, tension, woohoo. Not that that's a major issue. However, the major issue here is if they're loading it through this way, loaded against bottom threads, and you're using it this way, you're going to have about a 0.01% error. Right here, it's 3 pounds out of 25,000. You're going to have it. So the best solution is to talk with them and say, hey, I'm using this flat. I want you to load it flat. They're charging you X amount of money. They should replicate what's going on, and they should be able to do that for you. There should be no problems. And we have customers that want it loaded through the threads. Fine, that's great. We'll do it. No problem. It just needs to be communicated. Do you have a top lock that can be sent in with a force measuring device? Here's what happened. Customer sends in the device. We take notes, and we take lots of notes. They send in the device, and they don't include their loading pads. We see a shift in this data, and then they say, "Oh, wait, we forgot our loading pads." You know, actually, the whole situation that happened here was we told them we didn't have your loading pads, and they said calibrate it anyway. Then they saw a shift in the data and said, "Oh, we better send our loading pads." And said, "Okay." So what I ended up doing with having their loading pads, I ended up trying this different days, um, different scenarios, different blocks. Did it for about a week straight. Here was the best case scenario. With different blocks on the exact same day, there was a 0.307% difference between just the top block. So we recommend getting whatever you want. We will make top blocks if you need them, but whatever you want, get a top block, marry it with that load cell, and keep it with that load cell. Again, this was a best case scenario, just varying these two blocks in the picture to the right. What was the expectation? The expectation is better than 0.25 at capacity. So we are more than 10 times out of the expectation just from switching top blocks. As you can start to see, the right adapters like the hardness of the top block can produce large errors. We're going to discuss some major error sources that can be corrected with proper adapters. Really, calibration is all about keeping the line of force pure, free from eccentric forces. ASTM doesn't address it. ISO 376 appendix does. They say in section A 8.4 about having two ball cups, two ball nuts. They give you real good guidance. In compression, alignment is the key. So using a ball adapter, picture top right, if the machine has a ball adapter, it often yields the best results. This primarily because of centering. Other things could be friction, and some other things, less surface area, less friction in the frame. If a ball adapter does not exist, a spherical alignment adapter, picture top left, will help align the force. From the previous slide, some load cells are just more sensitive. Yeah, we have load cells that are more sensitive to alignment than others. So I showed you that tension link. Here's one that we get a lot. Tension links, improper versus proper pin diameter. This device is spec'd at 0.1% of full scale. Difference of 860 pounds shown here, or 1.72% error at 50,000 pounds from not using the proper size load pin. If you don't know, test it. You can take two different pin sizes and test it. Just make sure they're both safe to go to that capacity. Here's what we're looking at: tension member assembly, tension member adapters. This is our quick change. This is a patent pending set. What we've done is we've gone through all the manufacturers, most of the manufacturer spec sheets, and coordinated the proper pin size, laid them out in a table. So a person buys one clevis instead of multiple clevises, has all these pins. They can look up what they have that came in the door. I have a Tractel tension link X, and they can say, I need to pull this pin. I need to pull a 50 millimeter pin. You can say that simple, but it's not. Here's a good instrument for weighing. But if we start looking at spec sheets, we're looking at a 20-ton takes a 2-inch pin, and a 25-ton takes a 50 millimeter 197-inch pin. And you could say there's not much difference between 2 inches and 197. I will tell you that it is enough to put the instrument out of tolerance. Probably not your 1.72% error, but it's certainly enough to have 20 or 30 pound error, which can put on a 50,000 pound device, could kick the device out of tolerance when it's actually in. Shear webs. Remember I said about the hole? Any load cell with a hole, this hole right here, any load cell with this type of hole should be suspect. It's not good. If it's sent in without adapters, it's just simply not good. So our solution, because you have that thread depth problem, our solution is to purchase and lock in an integral adapter. If that cannot be done, secondary solution is pick a top adapter and always have it in the force measuring device. For tension, same thing. Send in a rod with a bolt on it. I mean, this is really where you're at. Button load cells. Morehouse button load cell adapters. Here's what most people use. Let's put this in the machine. If we look at the data here, the deviation was 10 pounds when we rotated it. Large spread of data. Averages are the same, surprisingly, which you can quote our good friend Dilip Shaw there, that's often says you can have your head in an oven and your feet in an ice bath, and on average you can feel fine. But averages do what he's basically referencing, and it's how averages hide the extremes. So averages hide these extremes. That's problematic. We have a situation here where the standard deviation without good adapters and alignment is 10.69, where that was improved to 2. Percentage error 1.045 was improved to 0.199. Our adapters improve the results by 525%. Now, which one would you want to send if you're the Cal Lab? How do you want to calibrate these, and what do you want to give to the customer? So button and washer load cell, above are pictures of butter and washer load cell adapters, which can improve alignment and yield better calibration results. We have a technical paper. Here's the link. One of the best paper awards at NCSLI. There was best overall, which it did not win, and there was best in category, which it won. I deeply honored to achieve that reward for this paper because it matters. And the paper was called "Without the Right Adapters, a Forced Calibration Technician is Nothing Short of Being Called a Miracle Worker." That is so true. So we talk about talk about standards, talk about adapters. Now we're going to talk about equipment. And the right equipment for force is going to mean to minimize off-center loading, bending, and torsion. To do this, force machines need to be plumb, level, square, rigid, and have low torsion. I know it says free of torsion, but torsion, as soon as you thread something together, you have some amount of torsion somewhere in almost all machines. So all these machines are designed with these 5 things in mind. Here, plumb, exactly true or vertical. A picture of our dead weight machine, 100,000 or 1,000-pound automated dead weight machine that is plumb. Weights hang in a vertical direction, and if they are out of plumb, they will introduce misalignment through vertical line of force. Newer machines, we're also stacking weights heaviest on top. That reduces the pendulum effect of the machines in the weight swing. So newer machines, heavier weights on top, and they are much more plumb, rigid, square, and free of torsion. The right equipment is going to be level. A device establishing a horizontal line or plane by the means of bubble in a liquid that shows adjustment to the horizontal by movement to center of a slightly bowed glass tube. Sometimes you put little levels down here on the machine where I drew a red dot. Pictured right is a 100,000-pound UCM. The upper and lower platen are ground flat and adjustable. Feet allow the end user to obtain a level condition. If level is not achieved, errors from misalignment will happen. Look at here. We calibrate this with a ball adapter, and there we have a ball adapter in use. So replicating how it's being used, this load cell comes to us. We calibrate it with these exact adapters. That gives you an expected performance. You put it in this machine, and after you put it in this machine, you can do your R&Rs, everything else. But what's brilliant about this machine is it free floats. So it has this ball and this yoke, it has some automatic self-alignment in it. It's just really a cool design. When you machine stuff and you can never get everything perfect. It takes a lot. Almost every machine has some type of misalignment in it. This machine acts better, as is with that ball, as it helps find center. And also, right equipment is square. You can look at this. This is our bench top, has 4 right angles. It's a 10,000-pound machine. Adjustable beam and bottom base form the 4 right angles. This reduces the chance of misalignment. The bottom screw is aligned to the top beam to keep the line of force as plumb as possible. Remember what I said before. We cannot get this perfect. As in a cow machine, that ball adapter helps. This is a very, very good machine. We are using alignment adapters per ISO 376, which overcome about 0.1 degree of misalignment. So we feel like we get everything good, and we're also doing some other things as shown in the next picture after this one. But rigid. Not flexible. If the loading surfaces starts to bend, all sorts of alignment errors can happen, which will impact the results. This is a newly designed USC 60K with reference load cell and Morehouse 4215 indicator. Top and bottom plates are reinforced to keep the machine from bending. So very rigid. Our older machines bent, we reinforce them. Newer machines have very, very low bending. And remember I said the other thing is torsion. The action of twisting or the state of being twisted. Free of torsion means free of being twisted when forces are applied. That is all done in here. Morehouse, what you're seeing is a PCM 2K with reference load cell. This machine has special bearings to keep things from twisting. Before putting in the bearings, the measurement errors were higher than 0.1%. We added the bearings, the errors became less than 0.02%, which is better than most transfer type machines. So this machine, there's a jack right here. It's a screw jack. Everything is about eliminating plumb level, square, rigid. We align these. There's a lot of alignment holes, and as well as that the torsion. If you're just bucking two things against one another in line, we have found lots of torsion in numerous machines. So therefore, you're starting to look at bearings and other things to help eliminate that torsion. Right calibration provider, the end of it. Hey, it's simple. Has equipment to meet your needs. There, decision rule. How measurement uncertainty is going to be accounted for. This is the graph. Lots of people have seen it. Anything to the right of the red line is measurement risk. In this situation, we have very, very high measurement risk. This actually came from aircraft scale with a very coarse resolution and a very tight accuracy. And no matter what you did, unless you hit nominal, you had to hit nominal with a dead weight machine or you were going to be out of tolerance. So right calibration provider. Here's what you look at things here. You look at the data. 10,000 pound device accurate, 0.5% full scale with a 0.01 resolution and 0.05 pound repeatability. Over here, the machines just aren't going to give you as good of repeatability, but they can get pretty good. But if we look at this, TURs, when we start looking at this ratio, TUR 22-to-1 versus the transfer machine 1-to-1. When we look at the expanded uncertainty, if we look at ANSI C540.3, if we look at that handbook, there's all kinds of considerations on what goes in the denominator. At a bare minimum per ANSI C540 is the calibration and measurement capability divided by the appropriate coverage factor that was used, resolution of the UT, and repeatability of the UT. There's other things in there. ILAC P14 also makes reference to having the short-term contributors. Those are resolution and repeatability as well. So we're basically using this denominator, which could have more than this in, but I'm using this because P14 kind of says this is the minimum. I know test value uncertainty people hate this, but it is how the standards are written. It is surely how ANSI C540.3 handbook is written, and it is certainly implied and even suggested, more than implied. It's in ILAC P14 if you read it and read specifically on short-term contributors. Primary versus secondary standard. We're looking at almost the same scenario here. I have a 10,000 pound device. My measured value is 10,000 pounds. Specification limit plus or minus 5. So I have this device. I want to send it to a lab. I send it to the lab with dead weights. I get a TUR of 20.833, and I get a graph that looks like this. I send it, and I'm using that equation. I'm using the CMC, the resolution and repeatability. I have another lab that I think can do the instrument. I send my instrument to them, and at 10,000 pounds, it reads 10,000. Guess what? In this scenario, when we take measurement uncertainty into account, our total risk is 4.55%. Our upper and lower are each above 2. Can we make a statement of conformance, a statement of compliance, a pass-fail? Can we do any of that if my risk is over 2%? Probably not. And furthermore, what happens if we move that? So both were at nominal. If we move it to 10,004, the lab with the low uncertainty calibrates it. They can still say your device was in tolerance, which prevents you from doing mass recalls. Whereas the other lab can't make that claim. The risk goes from 4.66 to 34.7. They have to call it out of tolerance. You look at ILAC G8. This is probably going to be a conditional fail or just a fail. It's going to be most likely going to be a conditional fail in the new ILAC G8. So, which puts it on the end user to evaluate things. And is the end user ever going to say 34.47% risk is okay? Here's what we're saying. A small relative expanded uncertainty is going to give you a larger acceptance window. So look at labs with low CMC uncertainty parameters. If they're low, you're going to have more chance at an acceptance interval being larger. And if the CMC calibration measurement capability uncertainty parameter is high, the acceptance interval is going to be less. So they're going to call more things bad, and there's going to be more to deal with as far as recalling equipment, all the fun stuff that no one wants to deal with. So right calibration provider has a measurement process uncertainty capable of meeting your needs, replicates how the instrument is being used. Very important stuff here. Uses the right adapters. Oh yeah, without the right adapters, showed you those errors. You may think you're getting something that's 0.025 and it's actually 0.3. Competent technician with training records. Yeah, that's always good. Follows published standards. How good do you feel about that cert that came out that was, 3-4 steps away from NIST and they're still claiming NIST? And how good would you really feel? Or how good do you feel about that lab that's assigning Class A low verified range of forces lower than what the standard allows? That's not too good. So is highly rated and reliable. And most important, all these are really important. So ask the right questions to help their customers make better force measurements. If you're not helping your customers, they shouldn't be your customers. Really, that customer should be able to come. You are the experts. Those customers should be able to come to you for help. You should be able to help them. If you can help them, you're going to do better. You're going to make the world safer. So Morehouse has reference force standards with calibration and measurement capabilities of better than 20 parts per million to conduct many tests on adapters and provide solutions that improve measurements for our customer base. The frightening part of this is not everyone in industry is part of our customer base, and several do not realize they have these errors. This is frightening. Many do not realize they have them. Can you imagine the company making critical measurements using a machine that is not plumb, level, square, rigid, and free of torsion? Guess what? They may say your instrument passes. They may adjust your instrument, and it may be 3, 4, 5% out. How about weighing something like a ton of uranium with the wrong pin size? That's great. You have to account for everything. You're going to weigh something that's going to give you yucca wherever it's going. You're going to weigh something, and you're going to be off by 1.72%, and you're going to tell the powers that be that we know our measurement capability is within 0.1. That's opening a door for a lot of risk. These measurements matter and can impact our safety. Anyone wanting continuing or a good book recommendation, Henry Petrosky, To Engineer as Human, one of the best books on measurement risk. I highly, highly recommend it. So please join us. I ask you, please join us in educating the people who underestimate the importance of following the standards, asking the right questions, using the proper machines and adapters. Using what was presented today, you can help us create a better, safer world by helping companies improve their force measurement. So please become part of our team, part of our outreach. Go out there and demand that people follow the standards, use the proper adapters, use the machines, and we will all be safer. Thank you. Thank you, thank you, thank you. And in the end, if you're not sure, somebody may have that question. I'm just not sure how good my machine is. Participate in a PT test, have 2 load cells calibrated in dead weight and compare them against each other, have 2 torque cells calibrated or a torque cell calibrated and compare it against another one. See if you get the right answers. Use the company that's going to give you the right answer, and then test your machine and see what you get in your machine. So here's our contact info. Please feel free to contact us with any questions, concerns. And again, thank you, thank you, thank you. Your time is valuable, and I appreciate you watching this and spending your time learning and bettering yourself. Be a better person, be a better lab, make better measurements, and help us make the world a safer place. Thank you.